talking about grading policy, I can show you where I'm very nice in the grading policy, where I am less nice. So the grading, uh, oh, using Zoom to see my screen completely, you know that you can have a speaker or gallery view, and then you have a slider in Zoom that can show you how much of, no, actually you don't need the slider here. Uh, I'll probably keep the screen more or less in this proportion. You'll tell me if you can read mostly what I'm showing. But by playing with parameter of Zoom, you can make me larger or smaller. Homework dates could be slightly massaged, a bit maybe extend if needed, and I'm not very big on being very punctual of time about when exactly you're submitting. I want you to submit in a way that allows us to grade and give you the answers, actually to give you the answer and then to grade whichever, and we cannot give you the answer before people that are planning to submit or submitting their homework. But if people will need a bit more time, I don't care. I care much more what you are submitting. I care much less about when exactly you are submitting. So if I will insist on dates, it will be because of other consideration, like I want to share the solution with you and I cannot until most people submitted or everybody submitted. Or at least that if you're submitted after I discuss the solution to something, you cannot submit this particular answer. So that's about the dates. Grading policies, now we'll have a midterm and we'll have a final. I assume that some people are doing better towards the end of the semester. Some people are actually under pressure towards the end of the semester because of other courses, projects. So I give more weight to the maximum of the two grades, the midterm and the final. But then I'm running every semester to cases of students that saying I'm perfectly happy with B or C and I already secured the B or C even if I get 0 at the final, so I don't want to study to the final at all. So at some point I decided to add this mean policy. I thought that I'm adding it just for formality, but actually there were cases that I did use this policy that you cannot do awfully bad in the final and still expect a good grade, where the exact detail of what are good grade are of course changes. But yeah, they don't take the final exam seriously. That's basically what it says. Don't feel that the course is all behind you, so you don't need to worry about it. So I'm not promising that somebody that got less than 70 in the final will get a D, but I feel comfortable or I feel covered not to give this person a C if you got less than 60 or less than 60 in the final. I can play it either way. Okay, we'll have 7 homeworks. 6 of I'll drop the lowest. That's standard. We'll have a midterm that we need to decide about the date and the format, if it will be over a examity or just that I'll give some window of time that you'll have to take this homework on GradeScope. One of the two will definitely do. I see that Jan is with us, our TA. Jan, do you want to introduce yourself, say a few words about what are you studying and what your expertise and experience? I caught him off guard, so I don't know if he is ready. Okay, once you're ready, let me know. I'm using OBS, which is very hungry to computer resources. So if you see that my voice starts, that the quality of the image start to degrade, or the sound and the voice are not synchronized, let me know, and maybe I'll avoid the OBS. Sometimes it happens, sometimes it's not. Also depending on how busy the network is. So that's about the policy. Any bureaucratic questions about how we're going to run the course? No, no. Everything will be out and published, of course. I'll try to have it more or less at the same time for all students as much as I can for fairness. Because, um, um, if there will be great reasons of why you cannot do it, or you are not in town and then you want to take the exam later, maybe you have two other exams at the same day, then let me know and maybe I'll let you take the exam a day or two later. I'm not too crazy about people. Uh, uh, yeah, let me know if you have another exam or more at the same day, or you're just traveling or something, and because of it you want to take the exam a bit later. Of course, I'll make you sign something that says I, I was honest in my answers, and that's it. And maybe I'll let you take it later. So, yeah, other bureaucratic questions? Uh, well, hopefully you saw my old videos of talking about the introduction. There is tons of things that I can put under the umbrella of uh, courses in theory, algorithms, lots and lots to put there. I basically went through expectation of the course here in this department and in other uh, top 20 universities. Some materials is very much out there, also based on what I thought is opening a window to, hey, I personally would have never thought about it. Look, what a great idea. Expose to it, put it in your toolbox. I will other criteria would that refers say I will teach you about linear programming and integer linear programming, which is not commonly taught in algorithms course. Again, linear programming and integer linear programming, it's not commonly taught in linear programming, but it's I cannot think about something that gives you more tool to solve problems that you might run into in your future life, either in industry or academy. So that's definitely important. It's enough algorithms there to justify being in this course. And there will be things that are just so very cool and so, again, mind-blowing of how they thought about it and are recyclable, at least. I hope that they are recyclable, that might help you later in your life. So that's how I picked the materials in the course right now. I think that summarizes the main thing about the intro. The one change that I decided about this semester, which you probably saw it, that I want you to type your homework in any process, any way to produce typed documents that you want, like LaTeX, which you can just use the template that I give you and write directly on it, make it, copy it to your own project, write on the LaTeX. That's one way. You can add figures handwritten. Figures don't need to be typed. You can just scribble on whiteboard and take a picture. That's fine with me. And then insert it into your LaTeX. You can make it with Words. You can make it with Google Docs. I don't care how, but make it so that I can take the. Eventually, you are submitting to GradeScope PDF, and I should be able to take a line from your PDF and ask ChatGPT if it's something that they created or not. Because of ChatGPT, I've changed the policies that handwritten is fine. That I so yeah, it's a bad thing. A bad thing that happens, but I need to be able to check your grades, the text that you are submitting. So once again, you're submitting a PDF, you're creating the PDF anywhere you want. Beside, don't create a text, take an image of it and submit the image into the PDF, where I cannot take the cut and paste words that you wrote, because then I'll just ask you to resubmit it again. I want to be able to trace if you cut and paste from ChatGPT or other materials. That being said, the course is completely, you are encouraged to talk to other people about the high level ideas. You have to write the homeworks yourself. That is, the algorithm is, think about the question in the homework, go home, think about the question in the homework, try to come up with your own ideas, and then meet your peers, virtually or relevant, live peers or whichever. Expose your ideas with other ideas. Eventually, when you got to the conclusion what is the best answer, go home and write this answer in your own words. That is, the later part is where you might get into troubles by writing the answers that somebody else wrote in, check.com, Overstack, etc. Well, you are aware, I am aware. Don't copy and everything. And I'm not shy of saying that the answers that you'll get from ChatGPT might deliberately or not be different than the answers that I expect from my questions. For example, the way that I'm teaching, later in the course we'll talk about the Frechet distance that I will teach you, and it's different than the classical Frechet. So if you ask for the classical Frechet, you'll get a different answer than what I'm speaking about. And I'll teach you because it's a fantastic example of good dynamic programming application. So deliberately or not, answers from other sources might be different than the answers that I'm expecting. And I think that covers the bureaucratic part of the whole course. Exams, usually you'll be allowed some amount of cheat sheet. Usually in class it's 4 pages written from one side, and questions are theoretical, related but not identical to question in the homeworks. That's pretty much the policies that I've used in the last 23 years. Question about homework 1? No, but the proof should be convincing. I'm not crazy on formality. Proof in this course should be argument, argument, argument. Why is this argument true? Either it's obvious or it follows from a different argument, and tell me why it's true, and so on. And eventually you need to tell me why does it prove what you are trying to prove. So rearrange it, but other instructors go much more formal about what consists of a legit proof. I don't try to impose it. What do I mean by saying that it's obvious why 2 follows from 1? Obvious is something that it's a social belief. It's not, it's not a We are not trying to go through the rabbit hole of explaining what's constitute of A followed from B in an obvious way. Okay. Yeah, yeah. Sequence of arguments that convince me that that's and and also worth mentioning that recursion formula, running time analysis, the course is not about them. The course is they are the obvious tools that we have to use to get to the cool stuff. But the course is not going to be about them. If you don't enjoy this part, I'm with you. Recursion formulas are important in the same way that going to the dentist is important. You need to do it. You're not expected to enjoy this part. There are plenty of cool and exciting things about this course. I don't think that that's included. Okay, the other questions, somebody asked for the question with water faucet. If you can assume that there is some minimum time that you can assume that T mean is at least 0.01 second, that's fine. You can assume that T mean might be much larger and you don't know it. I see that there is already some lag building. T mean might be is not smaller than a few microseconds, a few milliseconds. Okay. So somebody asked, and yes, you can do it, and it can help you. And once again, an algorithm that says I'll go to the faucet, I'll go to the faucet, I'll turn the faucet to the one side for t min seconds, and then I'll turn the faucet to the other side for t min faucets, and it should work. This algorithm is wrong. Why is this wrong? Because you don't know what is t min. That's a highlight. If your answer starts by I'll try both sides for waiting t min, there is such number t min, but you're expected to find or to guesstimate this number or get a good grasp about what this number. You cannot assume that you know this number. Yeah. Okay. So no other questions. Plan for today. Maybe I'll go quite quickly over the slides of SkipList and of hashing, at least starting hashing, much as time progressed, and I'll put the recording from previous year from the lectures that are explaining it a bit slower. So today I'll mostly give you highlight. Stable marriage algorithm, the TMA, the algorithm of Gale and Shapley. Any questions about it? I think that everybody, you'll have quite a few questions about Gale Shapley, the stable marriage algorithm in homework 2, including questions about how to fix the huge injustice about this algorithm. As we said, the main thing about the Gale Shapley algorithm is that the invariant was that each female ends up with the best male. Best in one sense, every female has a list of preference. She preferred number 17. That would be her top male. If he is not available, she prefers number 33 if he is not available, and so on, all the way to the lowest or the bottom one. Number 100 is her very last. And the main lemma of the algorithm is that each female ends up with the best male that has proposed to her. Only among these ones, if a male has not proposed to this female, there is no way that under this algorithm that they'll get married, which of course is huge, very annoying in very many ways, and that's the main message. Or a message is that the idea that under this algorithm females are not making proposals is something that I'll ask you to fix at homework 2 variants. We talked about optimality and pessimality of this matching. That, remember, when you look at the list of preference of each person, I'll pick one of the persons, let's say female J, and there are 4 people in this list. There is a top, there is a bottom, or the worst, and now again, and the being on the top, that's her first preference. That would be the highest preference. Male 17 is the one she prefers the most. Male 33 is the male she wants the least. And now there is a pessimal and the optimal male. 30 and 22. They might be the opt, they might be equal to each other, they might be the bottom. What is the definition of the optimal male for this female? What is the definition of the pessimal male? Is that the optimal male is the highest on her opinion. Every person has different opinions, but highest on her opinion amongst the male that ever proposed to her. We start among all the males. The opt one would be the highest that she can get in any stable matching, in any stable world. Not necessarily the TMA, not necessarily the algorithms that we studied for Gale and Shapley. In 30 is the highest she can get in any, under any stable matching that does not contain a rogue couple. 22, if he's a pessimal, meaning he is the lowest that she can get, again, in any stable marriage. If she will get 33 below her pessimal, it might happen in some matching, some marriage, but it's not a stable one. She plus another male would prefer to dump their dates and marry each other. That's what it means, that this guy is below her pessimal. And similarly, if she got 17, then presumably there is other rogue couple. What is a rogue couple? Couples that would prefer to dump their spouses and marry each other. Prefer in the sense that both will get something better on their own lists, corresponding lists. So don't confuse. It's very easy to confuse between the opt and the top. They might be the same, but not necessarily. And it's very easy to confuse between the pessimal and the bottom. Possibly it's the same person, possibly not. And what the TMA was mentioned is that if the male are the ones that making the proposals and the females are the ones that reject or accept, on one hand it looks very much injustice for the males, because the situation of a male is making a proposal, is a male based on the TMA, male 3. He is making a proposal to the top list in the TMA. But people, is a font large enough? Readable? Yes? No? Okay. Male 3. The algorithm says make a proposal to female 17. Female 17 got a proposal from male 3. At the moment she doesn't have any other proposal. The moment that she's getting somebody that she prefers over 17, she rejects 17, and then male 3, the moment that female 17 got a proposal from somebody that she prefers, let's say, male 3 is somewhere here in the middle of the pack among her preference. She got a proposal for male 3, and she tells him, maybe I'll marry you, maybe not, come back tomorrow. And he comes back tomorrow, and by tomorrow he's proposing to her again. He has to. If he proposed once, he has to propose again. And then she's saying, no, at the same time I also got a proposal. Oh, let's wait a bit. At the same time, she's also getting a proposal for male 5. Male 5 she likes less than male 3. Then she does not reject 5, and she still with male 3, still putting him on a spring. See, he's still a maybe. She says, I don't know, come back tomorrow. Next day, male 2 making a proposal to female 17. At the same time, male 3 is still making a proposal, and at this point she rejects male 3, and he crossed out 17 and goes down one list to female 20. That is maybe the next one, making a proposal, waiting for a while, building his expectation, hoping and hoping and hoping, coming up each day, still hoping until he's getting rejected and need to go down this list until he got married. So maybe it's devastated emotionally for the male because it's a list of rejections one after the other. On the other hand, when we look at the full picture, we see, and that's a proof that I ask you to review, that the male would be, that's a TMA, traditional marriage algorithm, also known as a Gale-Shapley. They got the Gale-Shapley algorithm. They got a Nobel Prize about a lot of observation, including this algorithm and its importance to economic Nash equilibrium and so on. That in the TMA, because of this processing, that females can only pick among the males that actually made a proposal, then in the TMA, each male gets his optimal female. But male 3 will eventually, if male 3 will eventually end up with female 13, then it's because she's the optimum. In no stable marriage, he will not end up with a better female than male 13. 20 is out of his league, 17 is out of his league, no matter what other people will do, as long as they don't change their preference. She is the optimum for male 3. She is the optimum for male 3, the best he can get in any stable world, and at the very same time, for female 13 that ends up married to male 3 is a pessimal one. Maybe he is a bottom of the list, maybe he's above the bottom, he's not as bad as being as a complete lowest, but in any stable world, he is the worst male that you can end up with, no matter what other parameters there are. So it's very, very one-sided. And we'll ask you to play with these parameters and understand and see how to fix them, at least partially fix them. Of course, first obvious attempt would be let's switch the rules of who makes proposals and who respects. Okay. There are various extensions to the TMA algorithm that are very obvious. Like there is what's called in literature the roommate problem of ignoring gender. Each one rank everybody else. Let's form matching out there. This problem is much harder, and the same algorithm can run into infinite loops. That's why I don't teach it. And in practice, the stable marriage algorithm is used maybe less, or at least less obvious in the stable marriage. It will, for example, the classical used is that to match intern to hospitals, each intern rank all the hospitals that he wants to do his internship in, her internship in. Every hospital rank all the candidates, and assuming that each hospital can meet only a few of them, let's have a matching which is stable. It's used together with other criteria in New York, as much as I know, to rank students and schools together with distances. And it has many extensions that are very, very useful, much less than just in the dating scheme. Okay, that's what I have to say. If you have questions about the proofs themselves, please follow the proofs, and I'll have a few questions about it in homework too. Okay, SkipLists, beautiful, beautiful data structures that some of you might have covered in 345. In 445, I ask you to go a bit deeper into understanding why SkipList works. And it first asks you, or the slides describe how to what our single linked list is. Just you have a simple linked list with a header, now a set of keys, and the last one either point to a null. If you don't like the word pointer or reference in Java, just think that each element has a next field, and the next field tells you that where in one array the next element is. So if I happen to store A at cell 106, then it will have a next field, and the next field will tell me the next element of the list, namely B, will be in cell 110, and the next of B, namely C, will be in 104, and back to 104. I don't care that the order is the same. The next is 0, implying that it's the last element in the list. That's just a normal linked list, just what is ahead, what is not. We usually store somewhere outside what is a pointer to the first element of the list. And sometimes we make the list doubly connected. Each element also points to the previous element if we want. What's more convenient? Why would we want doubly connected linked list instead of singly connected? Because it's easier to insert elements and delete elements at the middle of the list. You can have pointers, and then but not necessarily, but makes life sometimes more convenient when you have pointers both back and forth. What are we doing if we keep the list sorted? I'll assume here and in many other data structures, every field has some auxiliary data, like If it's a student ID, then maybe there is a student name, there is a student record, address, etc., etc. That's also auxiliary data. And there is a key, and the key is what we stored. If the list is sorted, then it's convenient to store also, waste tiny bit more memory and have the last element not be really part of the data, but have a key which is infinity, and minus infinity as the very first element, and again, it's not part of the data. I don't have a student with ID infinity. And now when we are doing find operation, what do? Here in syntax of C, we have a pointer that points to one of the elements, and as long as the key stored in this element is smaller than x, x is what we are looking for, we are moving the pointer to the very next element until we either find x or we are getting to an element that is too large. And then we are just returning p, which might be either what we are looking for or somebody that is already too large. What's the advantage of having the infinity and the minus infinity at the beginning is that if you write in C, at least normal C, you will write P equals null, and then you'll write P dot key, asking what is a field, what is a key field that P points to. When P is null, you'll usually get a crash dump that will crash your whole program, and it will be a headache to find where it's coming from. So how do we avoid it? Well, we either have to check in this code, did we get to the last element or not? Because if we got to the last element, then we cannot ask what is a key value, and we cannot perform P equal P next. Or we can store just the infinity and the minus infinity, and then it will never happen that we are getting to the very last elements. Whatever x is, it's always smaller than infinity. Okay, and that's how we are doing a find. Sometimes we want actually, when we are doing the find of x, not to find x itself, but to find one element before x. So I'm always doing look ahead of one element. I'm looking at P next key. So if P points to 21, then P next key will be 32. Right? And that's convenient if I I want to insert somebody right after x. It will be important when I want to do a delete or the insert of a new element or delete x. Then I actually don't want to know what is the element of x. I want to know what is the element before x. You'll see in a second why. Okay, I want to insert 35, and I didn't mention it. In this case, I want to keep the array sorted all the time, or the linked list sorted all the time. It's not an array. How do I do it? I want to insert 35. I'll perform find of 35, but now with the agreement that the while loop from the previous slide, this while loop, that's a while loop that I'm using for. I'm looking at P next key, which implies that if I'm looking for 35, then P will stop when P points to the 32. I would be in trouble if P points to the 37, which is the first element, which is larger than what I'm inserting, 35. Okay, so the next element is larger than 35, and my current element that P points to is smaller than 35. If I would find 35 itself, I would probably ask, does it make sense to double insert it if it's already in the list? And now I'm performing new operation in Java, or malloc if you want to go through basic C. Make a new cell that will contain the new element, put 35 inside, P1 points to this new cell, and make sure that the next of this element points to what comes after 32, the previous of 35. And now I'll just tell 35, hey, now you stop pointing to 37, instead you're moved to point to 35. Right? Stuff that you hopefully covered in 345. Am I right? Oh, news to anybody? Hello. Okay. Delete element from a linked list, even easier. All you need to do is find it. As usual, you're finding the element just before 35. And now you're just telling the element before 37, hello, go and point to the element just after the 37. Right? P, yeah, P, okay, and yeah, you're just moving the code from 32 to point to the element just after the 37. 37 is to be deleted. If you're nice, you will free P1 if you're in old style function. If you're working Java, garbage collection will take care of it eventually. Okay, but that's how you delete an element from a linked list. Just a reminder, because now when we had this uploaded to our mind, understanding SkipList will be much simpler. Because the reason that SkipLists are so great is because it's so simple to program. It's just like, it's slightly more complicated, but extremely simple to what we are doing on just a single sorted linked list. So rules about SkipList, I assume you've never seen it. Some of you did, never mind. I'll say it consists of several levels. Now in the SkipList consists of several levels. All the keys appears in level 1, including infinity at the end, again not part of the data, minus infinity at the very beginning, and here goes all the keys that are actually stored in the SkipList. 7, 14, 21. These are all the students at the university right now. So all keys appeared in level 1. Each level is sorted. Level 1 sorted. Level 2, which is above level 1, sorted as well. 7 is smaller than 21, that is smaller than 37, and so on. If a key X appears in level I, then it also appears in all the level below level I. Convoluted sentence. 21 appears, you still don't know why it appears, but it appears in level 3. It means 21 must appear, the key 21 must appear also in level 2, and it also appeared in level 1. So if somebody appeared in level 2, it must also appear in level 1. However, it's legit that 85 appears only in level 1, but not in level 2. So if we think about all the keys and distinguish here, keys are ID of students. Elements are the green disks that appeared in the SkipList. I have several elements, several disks that contain the same key, 21, over here. Okay, so if you think about it, think about all the elements of level 1, then inside this set of elements, elements of level 2 is a subset of the keys of level 1, and level 3 will be a subset of the elements of level 2, and level 4 will be a subset of the elements of level 1, of the keys in level 1, and so on. So if somebody appears in level 3 or level 4 or level 5, it must also appear in all the level before it. Next rule. The first element in each level is start by minus infinity. What is minus infinity? You're going to your language and just pick a really small number, or if it's float, there is, whichever language you are using, there is max float, min float, max double float, min double float, max int, min int. There are constants that are doing it. first element in the upper level, there is a pointer, some other field called top that points to the very first element in the uppermost level. Now the number of levels can change. Number of levels can be 1, it can be much larger, can be much smaller. It's no commitment about the number of levels. But all these rules always hold, no matter what. Okay? And once again, each level by itself is just a sorted linked list. Again, each level by itself is a sorted linked list, including the keys. Again, a key might appear multiple times, but in different elements. And in addition to know for each key what is the next element, I also have a pointer to the cell just below it, if there is one. So 71 will tell me that it's the lowermost level because the pointer down from it will point to null. There is nobody really below it. It can tell me that I don't have anybody below it. This element also stores the key 71, but the down pointer points to this 71. And so on for the 37s and so on. Okay. Each element in level 2 or more points has a down pointer to the element with the same key just below it. Elements in the lowest level have the down pointer, points to null. That's how you know it points to null. And the other part of the data structure that I need to store is a counter that stores how many levels do I have altogether. How many levels there are in the skip list right now, because it's going to change. Hint, it's or promo, we would like it to be roughly log n. But the whole deal of the skip list is that we are going to use, we are completely putting our career and luck on randomness. It's randomized algorithm. We are going to let the algorithm toss coins and make decision randomly, and still everything works usually very, very well. Here is an empty skip list. It's not the only skip list, but it contains the minus infinity, which is not part of the data. Infinity, only one level, that's fine. And you can have a few levels of this type, infinity and minus infinity. By the way, there is a link to the slide, you know, from the, if you go to the Google Doc and go to the syllabus, there is a link to the slides too. Now, how do I find an element in the skip list? That's why we think about skip list in a sense as some people like to think about it as a highway, as subway in New York, say. So you have the fast in the same stations. You have the fast train that stops at streets 21 and 37, and that's the only streets, only station that it stops. You have a slightly slower train that stops at 7, 21, 37, 71. You have a much slower train that stops at almost at every station. At street 7, 14, 21, 32, and so on. How can you get, you want to get to the 85 street. How would you do it if you're in a hurry? You'll take the fast train that will stop as rarely as possible, or in other words, the fast train allows you to jump all the way to street 21 and will allow you to jump all the way to street 37, jumping over all the stations that you have in between. And now you take off at street 37, use the intermediate train to go from 37 to 71. You're not continuing because then you'll shoot way too far. So you're taking off at this street, going down, and use the slow street to go to 85. And that's exactly how skip list works. We called it a skip list because every pointer which is not in the lowermost level tells us I can jump over a big chunk of information. Again, I can skip over a big chunk of information that I don't need to visit, to carefully visit and know exactly what it is. Let's think about it. I'll show you a search tree. I'm doing find of 20 in this search tree. You are trying to find it without a blur. I'm doing find of 20 in this search tree, and you're going to the root of the tree, and you see that in the root of the tree it contains 17, and because you know the rules of search trees, you know that everything in the left subtree is smaller or equal than 17, while you're going to visit 20, implying that I don't care what is written in the left subtree. I can jump over all of it and go immediately to the right subtree. Similarly, in the skip list, I can find 85 by visiting all the nodes in the lowermost level, but I can jump over pieces of information that are not relevant to my search. I want to find 117. I will use the highestmost level, the top level, to try to go as far as I can without overshooting. There are no back pointers. There are no pointers that points backward. So if I got in the lowermost level to a key that contains something that is more than 85, I don't have an elegant way to go backward. I'll have to, so I am careful not to overshoot. So let's look at the pseudocode. I start from the top, and as long as the P next key is smaller or equal than X, again, what is P next key? Always look one element ahead of what P points to, and ask what is a key one element ahead. If it's still smaller than X, then P equal P dot next. Otherwise, what happened when you got to an element where the next element is already too large? If there is a way to go down, then go down. If you are already in the lowermost level, then return P. And the function that calls the find will decide based on the P, the pointers that you return, decide what to do. Otherwise, there is a way to go down. You're not in the lowermost level. Then go down one level and start the while once again. Let's see how it works. I'm looking for 117. 116, 117. What happens? Start when P points to this minus infinity. Next element still smaller than P, so I can move to the next element, smaller than 116. Next element still smaller. Next element is infinity, too large. Go down. Next you can move in the intermediate step, intermediate range. One step further because 17 is still safe to move to, but it's not safe to move to the next element. Too large. Go down. Go to the 85, and in this case you stop. And you stop both if the next element is 117, which is what you're looking for, or you're looking for 116, which is not in the skip list. Either way, you're still returning this guy as a last guy, as what this pseudocode returns. Make sense? Okay. So it's clear we are always trying to stay in the highermost level or in high level as much as we can, as long as it's safe to move to the next element in this level, and it's always sorted. Now I want to expose you to something that I used. I didn't see it in other textbook, and I'll call it a perfect skip list. It has a bit of application, and I'll tell you when would you actually use it practically. But right now I'm presenting it just because it's very easy to prove properties about it versus properties of real practical skip list. Here for the perfect skip list, I'll show you just nice properties of what's what the search looks like, how much time, and so on. So how do I create a perfect skip list? I first create the lowermost level, and I'll put each and every key in the lowermost level. And as usual, ends with infinity, starts with minus infinity. So I start from the bottom, creating the lowermost level. Now I'm scanning this level, the lowermost level, level 1, and I decide that the first element will be promoted to level 2. First element promoted to level 2. Second element not promoted. And remember, if you are not promoting to level 2, then you cannot find yourself in level 3 or 4 or 5. You have a chance to make it to level 3 only if, it's not if and only if, but only if you made it to level 2, then you have a chance to make it to level 3. You are not jumping up. So going down over the lowermost level, and I decide promote, don't promote, promote, don't promote, promote, don't promote, and so on. Every second element is being promoted to level 2. And every second element, but now starting from the odd one, is not being promoted. So in level 2, I have about half of the elements, and half of the elements plus minus 1. And now I'm doing the very same thing, going through over level 2 and promote every second element. So first one, promoted. Second one, not promoted. Third one, promoted, not promoted, promoted, not promoted. But infinity has some privileges. It is promoted nevertheless. And then I'm going to the next level, do the same exercise until I am done with, I don't have any elements to promote or just one element to promote, and then I'm done. That's a perfect skip list. So the rule of the perfect skip list would be that if you are on level I, no matter what is I is, 1, 2, 3, dot, 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 level I, and I have 3 elements one after the other, X, Y, and Z. By the way, word of warning, that's my Z. It looks like, you'll see it in the slides, that's my Z. The sun is moving, so I adjust. X, Y, Z. If that's a perfect skip list, then you'll usually say X will be promoted, so X will appear also here, Y will not be promoted, and Z will be promoted. Okay. Out of every 3 consecutive elements, only one is, out of every 2 consecutive, only one is promoted, and out of every 3, you're skipping one and just take